Thank you for your patience. All right, so you would plug in these t values. Just when you go to plot it, you kind of need to ignore that part of the chart because you're still plotting on an x, y coordinate plane. T is just the parameter that x and y are in terms of. So these are the points we're going to plot. And I made it big enough so that it would, the grid big enough so it would fit here. So -7, 12. And then -5, 3. Did you get a parabola? Oh, you guys did say that. You got a hook, right, is what we called it. And then -1, 3. So like this, did you draw the orientation on there? So we started here, and then as t goes along, it's going this direction. I like that with a little like arrows on it. That looks cool. All right, you would want to solve for t in this equation because this one has a squared, and then stuff gets messy when you square root. So I would solve for t over here, add over the 3, divide by 2. And then you're going to take that and plug it in for t over here. So you would get y equals 3 times all of that squared. You could have fun with the algebra of squaring that out if you felt like it, but there's a 1/2 in there, and you square that, you're going to get a 1/4 and then have to distribute that. I believe that if I made you guys do it, you could do it, but at a certain point, it's like, what are we trying to do here? Okay, so did that one go all right? We're remembering this, that's awesome. All right, so this one, I left a lot of space here. You don't really need that much space. Here's a rectangular equation that goes through, we wanted to go through this point and just make sure that that's true. Like, would the 0.31 be on this line? Like if you plug in 3, do you get 1? Yeah, okay, so that's true. We just want to write parametric equations, x equals and y equals, so that we go through that point when t is 0. We're going to go through that point no matter what, but we're saying specifically when the parameter is 0. I could have said, make sure you go through that point when t is anything and just pick 0 because that makes it easy. So I would make x be t plus 3. If you plug in 0 for t, you're going to get 3. And then just take that and plug it in for x in the equation. So it would be 2 times t plus 3 minus 5. So what is that going to be? 2t, what is plus 6 minus 5, so plus 1. You're all just kind of staring at me. Does that mean we're okay? Okay, well, I just put those on there to review what we did 2 classes ago because I know we had to start this unit and then go back and take the other test. And I know that that's difficult. So I really appreciate you guys like being cool about that. I just didn't want to make you take the test on a shortened day. All right, so here's the new stuff. Here's our lesson for today. Now we're going to do derivatives with these. Here's the pep talk. Quotient rule hasn't changed. Product rule hasn't changed. Power rule hasn't changed. None of the trig derivatives have changed. Chain rule hasn't changed. You just now have 2 of them. There's an x and a y. Does this make sense? Like it's going to look scarier because there's 2 of them, but like none of that has changed. If you could take a derivative before, you can still do it now, right? So if we have x equals some function of t and y equals some function of t, then the slope is, and so we're going to write dy dx, and you're just going to do the derivative of y with respect to t over the derivative of x with respect to t. So it's dy dt over dx dt. And I realize that looks like a mess because you have like 2 fractions inside of another fraction. But essentially, you just do the derivative of y, put a fraction bar, and then the derivative of x. Is making sense? Okay. And then the second derivative, so we're going to have these little 2's in here. So your second derivative, you're going to do the derivative of what you just did. And I want to make sure I put all the notation correctly. With respect to t, because t is your parameter. So you're going to do the derivative of what you just did. Like usual, I mean, that's what a second derivative is. You do the derivative of what you just did, but you have to divide by dx dt again. The way I kind of reconcile that in my head is, do you remember when we did velocity and acceleration? Units for velocity would be like feet per second. What were your units for an acceleration? Feet per second per second. So that's why you do the like per dx dt again. Is that like sitting well with everybody, like common sense was? Like that makes sense, right? Horizontal tangent line is going to be when dy dt is 0. That's because that's the numerator, 0 slope. So horizontal tangent line is going to be when dy dt is 0. Vertical tangent line is when your denominator is 0. So that's when dx dt is 0. So numerator is 0. That gives you a horizontal tangent line. Denominator is 0. That gives you a vertical tangent line. Are we all still on the same page? All right, so we're going to use these two parametric equations. We have x equals sine of t, y equals cosine of t. T is going to stay between 0 and 2 pi, so once around the unit circle. Find dy dx. So we are going to do dy dt over dx dt. So we're going to do the derivative of this one. All right, so derivative of cosine. Negative sine, so negative sine of t. And then we're going to do derivative of x. So derivative of sine, cosine. And then we can reduce that. Sine over cosine gives us what? Tangent. So this would be negative tangent. All right, so that's our first derivative. So second derivative. We're going to do the derivative of what we just did. That's not like new. But then you have to divide by dx dt again. And again, the way I think of that is like feet per second. You're dividing by that again. So derivative of tangent, secant squared. So it will be negative secant squared. And then you have to divide by dx dt again. So what did we say dx dt was? Cosine, good. And then we can actually simplify that a little bit more as well. Cosine would be 1 over secant. So if you have negative secant squared over 1 over secant, it's going to be negative secant cubed. They're reciprocals of each other. So if you flip the cosine, does that make sense to everybody? Like if you flip that, then you have a third one. All right, and then letter C. At what points is there a vertical tangent line? That means we're going to set dx dt equal to 0. So dx dt we said was cosine. And our t values only go from 0 to 2 pi, so just once around the unit circle. So we're looking for places on our unit circle where cosine is 0. Here, I'll draw you a unit circle. Cosine's the x value. So there's 2 of them. Where is cosine 0 on your unit circle? Yeah, perfect, good, right there and right there. So pi over 2 and 3 pi over 2. I think is all that one asked for. Oh no, it says at what points. We didn't actually find the points yet. We found the t value. So we need to find the coordinate points x, y. So we're gonna have to plug these values back in up here to get the points, okay? So first let's plug in pi over 2. Sine of pi over 2. That'll be 1, comma, and then cosine of pi over 2 is 0. So that's one of them. And now we're going to plug in 3 pi over 2. That's down here. Sine of 3 pi over 2 is negative 1. And then for y, cosine of 3 pi over 2 is 0. So those are the 2 coordinate points. Now I just want us to take a minute and type it in the calculator just so that we can visualize that, just to see it as well. So what you need to do if you hadn't, or if you changed it back since last time, is go to mode. It's right next to second. Go to mode and make sure that you're in parametric mode. Make sure that PAR is highlighted. And then for x, we're going to put in sine of t. And for y, we're going to put in cosine of t. Oh, frozen again. All right, did we get those typed in okay? All right, now you're going to go to window. We want our x's to be from 0 to 2 pi. Or no, I'm sorry, not the x's, the t values. You want the t values to be from 0 to 2 pi. I just always leave the t step at 0.1. Do you remember I showed you last time, if you make it too large, it ends up being kind of boxy because it only plots a point like every how often you put it. And then Evan, didn't you make yours like super tiny and it would like never work because it was trying to put like so many tiny points on it. Anyway, 0.1 is good to go with. I think I have mine at -5 to 5 for both of these. That should be good. And then I'm going to hit graph. So it's a circle with a radius of 1. And so does it make sense that we have, what did we find? Vertical tangent lines at 1, 0 and -1, 0. Do you see how we would have vertical tangent lines here and here? If I had asked you for horizontal tangent lines, they would have been at 0, 1 and 0, -1. Just want you to make the connection with seeing it visually. I like a picture. Okay, but you're all staring at me like I got it in school. Move on. All right, so now I'm giving you these ones. These don't have trig. We've got square root of t and then 1/4 t squared minus 1 for all t values. So first find the derivative. So dy dx. We're going to do dy dt over dx dt. So what is our derivative of y? Good, that'll be 1/2 t over, and then derivative of x. Oh my gosh, does anyone remember derivative of square root? If not, I'll tell you. Good, perfect. 1/2 square root. So let's clean that up, because the next thing we're going to be asked for is the second derivative. So you kind of want to simplify that down before you start trying to do the derivative of that. When you have this in the denominator, it's going to reciprocate. It's exactly like we did up here with the cosine. And we ended up with secant cubed. This would be 1/2 t times 2 square root of t. So the kind of nice thing about that is the 1/2 and the 2 are going to cancel. And then you have t times square root of t. All right, that's t to the first, so one of them. And then this is t to the 1/2. So we have 1 and a half. Are you coming with me on that? Now, you would never see t to the power 1 and a half. We would write it as what? Yeah, 3/2, good. All right, so now our second derivative. You're going to do the derivative of what you just did. That's what a second derivative is. And then just divide by dx dt again. So what would be the derivative of what we just found? Yeah, good. It would be 3/2. And then you would subtract 1 from the power. So 3/2 minus 1 would be 1/2. And that would be square root of t. I'm just writing as t to the 1/2 to like kind of show the middle step there. All right, over. And then we have to do the derivative of dx, or we have to do dx dt again, the derivative of x. So again, that would be 1/2 square root. So same thing, this is going to end up being 3/2 square root of t times 2 square root of t. So the 2's are going to cancel. And the roots are going to cancel. And so what's like the final answer for that? Like once you simplify that down? 3t, perfect. So t to the 3/2 for our first derivative and then 3t for our second derivative. Find the slope and concavity at the points 2, 3. Slope, that's the first derivative. Concavity, that's the second derivative. Here's the thing. You have to plug in t and you're not given t. 2 ways you can do this. You can either set x equal to 2 and solve it, or you can set y equal to 3 and solve it. You want to pick whichever one is easier. So which one looks easier to you? Yeah, I would do x, all right? So we've got square root of t equals 2. If you were to set y equal to 3, you will end up with the same thing. It doesn't matter. You just want to pick the easier way. And so t is what? T is 4, okay? So we're going to find our first derivative at t equals 4. This will be our slope. So that means we're going to plug 4 in right here. Okay, 4 to the 3/2. 4 to the 1/2 would mean square root of 4. So square root of 4 would be 2. And then to the 3rd power. So 2 cubed will give you 8. Again, it was 4 to the 1/2. That'd be square root of 4. That's 2. Cube that, you get 8. I didn't like write this in the question, but where I'm headed here is 8's a positive number. If your derivative is positive, what does that mean your graph is doing? Positive derivative. Increasing. Good. That's like where I was headed with that. All right, and then let's do the second derivative at t equals 4. All right, so we're going to plug in 4 right here. 3 times 4, that's going to give us 12. Again, that's positive. And so if your second derivative is positive, what does that mean is going on with your graph? concave up. So just throwing that in there to review, because again, none of that information has changed. Like that's all still true. And then D says write an equation. All right, what two things do we need to write an equation? Point and a slope. I gave you the point. We just need the slope. The slope comes from the first derivative. Oh, but we need to find T again. I gave you the point, but we don't know what T is. So again, you could set X equal to 4, or you could set Y equal to 63. It doesn't matter. You want to pick the one that's easier. So I would set X equal to 4. So square root of T equals 4. And so what is our T value for this point? Be 16, good. So our slope of our tangent line is our derivative at T equals 16. All right, so let's see, we're plugging 16 in right here. So again, to the 1/2, that means square root. So square root of 16, 4, and then to the 3rd. So 4 cubed is 64. So this is your point, this is your slope. Just assemble the equation. It's been a while since we've written these. How do you write the equation? It would be y and then what? 3, good, equals. Perfect. So again, writing equations of tangent lines hasn't changed. That information's all still the same. Throw it wherever. Everything's a mess and I will figure it out later. Everything's, you're just telling me, everyone keep telling me everything's going to be okay. Miss Cole is having a week. If you couldn't tell. I'm just having a week. It's all going to be okay. All right, peace. All right. I think this is the last one I put on here. This is a short lesson because I mean, if you can take a derivative, you can still take a derivative. All right, so we're going to use these two parametric equations. Time is from negative pi to positive pi. Oh, this says write both tangent lines equations at the point 0, 2. We're going to write them, and then I want us to look at this one on the calculator because you can see there's actually going to be 2 tangent line equations at the same point. So here's our point. We need our slope. That would be the derivative at whatever t value. So I need the t value. You can set x equal to 0, or you can set y equal to 2. You want to pick the one that's going to be easier. Let's see. Oh, that's a typo. I'm sorry. This equal sign right here should be a negative or a subtraction. I apologize. Yeah, y is going to be the easier one because there's only one t value in it. So there's only, yeah, like that's going to be the simpler one. So let's set y equal to 2. 2 minus pi cosine of t equals 2. So we're going to set that equal to 2 and solve it. So what would you do to both sides? Subtract 2, you end up with 0, which is fantastic. Because you would next divide by negative pi, but 0 divided by anything is 0. And I feel like this is the one we just did on the other side of the paper, isn't it? We get t equals pi over 2 and 3 pi over 2. So there's going to be 2 answers. We're going to get, oh, you're right. So it's going to have to be just pi over 2. Oh, you're right. Negative pi over 2. Oh, okay. So there will still be 2 of them. It'll be negative pi over 2 and positive pi over 2. There we go. I knew there were going to be 2 of them, but you're right. Because of the domain for t in between negative pi and positive pi, it's going to have to be those 2. Thank you. Crisis averted, because that would have messed us up later. All right, so we're going to plug those into the derivative. Oh, so I guess we need to stop what we're doing and go find the derivative. It's going to be dy dt over dx dt. All right, so let's do derivative of y. 2 is a constant, so that's gone. You can kind of ignore that. Derivative of cosine. Negative sign, good. So the negatives are going to cancel. It'll just be pi sine of t. And then over dx dt, so we're doing derivative of x right here. Derivative of 2t would be 2. And then minus derivative of sine would be cosine. So pi cosine of t. All right, so let's do the negative pi over 2. So negative pi over 2 on your unit circle, you've rotated backwards. That's going to be this point down here. Sorry, I always draw it because I like to have a visual to see it. So we rotated backwards. That's going to be right down here. So sine at that point would be what? -1, good, times pi, negative pi. And then down here, cosine at that point, cosine's the x value, so that's 0. This whole thing's going to go to 0. And so you would just get 2. I think that's kind of interesting. We plugged in negative pi over 2 and we got negative pi over 2, which is interesting. All right, and then let's do the other one. This one's going to turn out the same way. I think that's interesting. Just kind of like a, yeah, no, just this problem. It's a coincidence. It's a cool coincidence though. All right, if you plug in pi over 2, now we've rotated in the positive direction. So we're up here. We're plugging into the derivative right here. So sine of pi over 2 would be 1 times pi is pi. And then cosine of pi over 2 is 0. This whole thing goes to 0. And so you just get 2. I didn't actually finish answering the question yet because what did it ask for? The equations, okay? So for this point, one equation would be y minus 2 equals negative pi over 2 x minus 0. I always write the whole format. I realize that that's 0, so you technically don't need that part, but I just always put it. And then the other one would be y minus 2 equals positive pi over 2 x minus 0. Let's look at this so you can see why there's 2 of them. I think it's kind of interesting. How am I doing on time? Are we good? Okay, we got plenty of time. All right, go ahead and go to your, I guess it's not y equals, x equals and y equals, your parametric equations. Clear those out and then type in these ones. So 2t minus pi sine of t. And then 2 minus pi cosine t. And I'll pause there a minute, wait for everybody to get that, and then we'll go to the window. All right, I'm not hearing the tapping anymore. Okay, so go to window and we want t to be negative pi to positive pi. Leave that as 0.1, and then I just always leave it -5 to 5. That should be good enough. If it's not, then we can always adjust. You know, like the window is just something you need to mess with until you can see the whole thing. Oh, is it cool? It's a loop-the-loop. Isn't that neat? That's cool, guys. That's cool. You can disagree, but I'm right. That's so cool. So we wrote tangent line equations at this point. So do you see why there's 2 of them? Like this would be the positive slope one, and then this would be the negative slope one. That's cool. That's so cool. Anyway, that's why there's 2 of them. This is the one with the slope of positive pi over 2, and then the slope of negative pi over 2. And that's cool. It looks like a little teardrop or something. All right, last one. At what points is there a horizontal tangent line? What are we going to set equal to 0? Good. dy dt is 0. dx dt is vertical tangent line. dy dt is horizontal tangent line. All right, so dy dt, derivative of this right here. We found it already, right? Pi sine of t. So you would divide by pi. 0 divided by anything is just still going to be 0. And so t would be 0. Again, we're stuck in between negative pi and positive pi. So t equals 0 is the t value that we're going to get there. Now you can't stop there because it says at what points. So you have to take that 0 and plug it back into both of these to find the points where that actually happens. And again, then we'll look at it on the graph. All right, so if we plug in 0 for t in the x equation, what are we gonna get? It would just be 0. Yeah, sine of 0 is 0, 2 times 0, 0, 0 minus 0, 0. All right, over here, cosine of 0 is 1. So this would be 2 minus pi. Pi is 3.14 about, so 2 minus 3.14 would be like negative 1.14. You guys following me there? Okay, because what we're going to do is look on the graph. Do you see how right here there would be the horizontal tangent line? And that's happening at 0, 2 minus pi. I realize it looks like 0, negative 1, but it's actually 1.14. It's 2 minus pi. Like that's where your horizontal tangent line is. I like making the connection to seeing it visually on there. Like, I don't know. I like seeing the picture. I think it's cool you can type those in.